Welcome to today's Explainer. We're looking at the ESP32, from anatomy to action. We're going to take the totally abstract, invisible concept of computer code and transform it literally right before your eyes into a functioning, physical, electronic circuit. So if you've ever wondered how smart devices actually work from the inside out, well, let's get started.
It's kind of the ultimate question in modern electronics, right? How exactly do you make the digital world interact with the physical world? Okay, let's dive into this. Imagine zooming in, way past the plastic casing of your smart home gadgets, right down to the microscopic level of the circuit board. What we're looking at here is a macro close-up of a tiny, incredibly powerful engine that literally makes the Internet of Things possible.
Meet the ESP32. Designed by Espressive Systems, this is a low-cost, super energy-efficient microcontroller that fully integrates both Wi-Fi and Bluetooth. But it's really important to understand that this isn't just some simple chip. It is a highly capable IoT brain. It's the direct successor to older boards like the ESP8266, and it essentially supersedes those older non-wireless microcontrollers by packing immense connectivity into one single package. As we explore it, keep an eye on the labels popping up to highlight its core anatomy.
Now, what's really interesting about this slide is the sheer processing power packed into such a tiny footprint, manufactured using a microscopic 40-nanometer process. We're talking about a Tensilica X-Tensa dual-core 32-bit LX6 processor running at a blistering 240 MHz. Plus, it boasts 520 kilobytes of SRAM alongside native support for 2.4 GHz Wi-Fi and Bluetooth version 4.2. I mean, that is an absolute powerhouse of specs for something the size of a postage stamp.
All right, let's take a visual tour of the PCB's anatomy. As we pan across the board, the very first major landmark you're going to notice is this large metallic square. This is the ESP32 module. Think of this thing as the vault. It's a shielded enclosure specifically designed to protect that powerful dual-core processor and the embedded flash memory from any external electromagnetic interference.
Moving just slightly over to the edge of that shielded module, you'll see a really distinct, zigzagging copper line printed directly onto the board itself. That is the trace antenna. Now, it might just look like a simple geometric pattern, but this tiny detail is exactly what enables the seamless wireless data communication we just talked about. It's literally beaming your Wi-Fi and Bluetooth signals out into the world.
Panning down to the bottom edge, we find a very familiar sight, the USB port. Depending on your specific development board variant, this could be a micro USB or a modern USB-C connection. But either way, this port serves as the primary physical gateway between your computer and the microcontroller. It provides the necessary power to wake the board up, and it's the exact pathway we'll use to push our code directly into its memory.
But here's the catch. USB signals and microcontroller signals don't natively speak the same language. So right behind that USB port is a tiny, unsung hero, the USB to UART bridge. This is usually a chip like the CP2102 or CH340, and it acts as a crucial, high-speed translator, handling transfer rates up to 3 megabits per second. It basically ensures that the code you compile on your PC is properly converted and delivered flawlessly to the ESP32.
Right next to our translator is the power manager, the voltage regulator. See, your USB port spits out 5 volts of power. But here is a surprising and honestly vital fact. The ESP32 operates strictly on 3.3 volt logic. This is completely different from some of those older 5 volt Arduino boards you might be used to. If you hit the ESP32 chip directly with 5 volts, you'd fry it. Or, as hardware engineers like to joke, you'd let the magic smoke out. So this regulator safely steps that 5 volts down to a clean, steady 3.3 volts.
Finally, spanning both sides of the board, we've got the general purpose input/output, or GPIO pins. The ESP32 chip features 34 of these, allowing you to connect sensors, LEDs, displays, you name it. Each pin can safely draw a max of 40 milliamps of current. And remarkably, 10 of these pins even feature built-in capacitive touch sensing. That means they can detect the electrical charge of human skin, which is exactly how smart home touch panels work. One of them even acts as a Hall effect sensor to detect magnetic fields. Pretty cool, right?
Okay, let's move to and see how this builds. As we pan over to our digital breadboard, let's see how all of this translates into an actual working project. First up, we place a basic red LED and a 220 ohm resistor right onto the breadboard. That resistor? Totally mandatory. Without it, we wouldn't be limiting the current, and our LED would instantly burn out.
Next, we route a jumper wire from the ESP32's GPIO2 pin to the longer leg, the anode of the LED, passing through our resistor. Then, a second wire connects the ESP32's ground, or GND pin, back to the shorter leg, the cathode, to complete the circuit.
Now we've got a physical circuit, but it needs instructions. Check out this snippet of C++ code floating into view. It reads, digital write, lead pin high. So the crucial point is, this is where the magic happens. When the ESP32 reads this exact line of software code, it triggers a physical hardware response. It commands the microcontroller to send a logic high signal, which, as we learned earlier, is exactly 3.3 volts, straight down that wire connected to GPIO2.
This floating code is part of the famous Blink sketch, which is widely considered the hello world of hardware programming. It basically has two main sections. First, the setup function runs just once to configure GPIO2 as an output pin. Then the loop function takes over, and that runs forever in a continuous cycle. It turns the LED on with high, hits a delay of 1000 to wait for exactly 1000 milliseconds, or 1 second, then turns the LED off with a low command, waits another second, and just repeats that endlessly.
So, we have our meticulously designed 32-bit hardware, we have our carefully wired breadboard circuit, and we've got our C++ logic ready to go. What happens when we actually power it up? Well, watch closely as we virtually supply power to the setup. You can see the energy flow from the USB port right through the regulator into the ESP32 and down our jumper wires as an active, glowing pulse of current.
And there it is, a perfectly rhythmic heartbeat. The red LED on the breadboard blinks on for 1 second and off for 1 second. And this brilliantly illustrates the magic of microcontrollers. Just a few lines of digital text typed on a computer have successfully dictated the flow of electrons in the physical world, bringing our little circuit to life.
By understanding the anatomy of the board, wiring up the components, and grasping the code, you've completely bridged the digital and physical world today. And honestly, a blinking LED is just the very beginning. With 34 GPIO pins, capacitive touch sensors, dual-core processing, and built-in Wi-Fi and Bluetooth, the possibilities here are virtually limitless. So the only question left for you is, what IoT device will you build next? Thanks for exploring the ESP32 with me today on this explainer, and keep building.